in between if you are not able to see the slide. Point number one. This point number one is the entry here. Okay, entry to the converging portion. You can see the area coming down. Okay, so that is the converging portion, and you can see that at state point number two, the area is minimum. So here the area keeps on decreasing, and it is minimum at this particular point. And then, so at this particular region, the area is minimum, and then it once again the area starts increasing. So this region we call as the throat, and this is your exit. Okay, and because you're not studying gas dynamics, this region is where we call as the region where you have the sonic condition where your Mach number is equal to 1. And I have told you Mach number is velocity of the fluid divided by the velocity of sound. So when Mach number is equal to 1, your velocity of the flow will be equal to the velocity of sound. Okay, so that happens here at throat. And uh, we usually take a lot of pressure ratios, and P2 by P1 is the critical pressure ratio at the throat where your flow rate is maximum. Okay, and this P2 corresponds to the pressure in the throat region, and this P1 corresponds to the pressure at the entry. Okay, and because your Mach number is 1 at the throat, people also call this P2 as P star, um, a critical condition, which we study in gas dynamics. You can just understand that this pressure is called the critical pressure because that is the pressure at the throat, and it is sufficient to know that at this particular point of time. Okay, so that is what you see in the next slides, which I showed you here. So instead of writing it as uh, P2 by P1, they have written it as P star by P1. P star is nothing but P2, and that is the critical pressure ratio, which is 2 by n plus 1 whole to the power n by n minus 1, which we can see after a couple of minutes. So this n is nothing but if it is an isentropic process, this n is nothing but your gamma. Okay, and that gamma value is 1.135 in case of the saturated steam, which means when your steam is on the saturated vapor line. So if your steam is on the saturated vapor line, it is called as saturated steam. Okay, so for that condition, your n is 1.135. You can substitute and see 2 divided by 1.135 plus 1 whole to the power 1.135 divided by 1.135 minus 1. And if you just put this in the calculator, you will get 0.577. Okay, so this is what you will be able to see. So in a similar way, you will be also able to find out the values for, so you will also be able to find out the values for superheated steam, where the gamma value is 1.3 and the critical pressure ratio becomes 0.545. Okay, so this is 0.545 when gamma is 1.3. When gamma is 1.113, it's 0.582, and that is for wet steam. And for air, gamma is 1.4, and you get this as 0.528. Okay, right? Okay, so now the whiteboard is ready. It's not installed yet. Sorry about this. So because I have got the Adobe Reader in the laptop, I forgot that it's not there in my system. So I'm not able to use the pen here in the system. Okay, so let that get installed and we will go to the derivation part. Okay, so we were here. Where were we? We were deriving it. Okay, over here. Okay. So we said the condition for maximum discharge is dm dot by d of P2 by P1 equal to 0. And we said A2, 2n by n minus 1, P1 by V1, all these fellows are constants with reference to P2 by P1. Okay. So let me do this. Okay. So now, when I'm going to differentiate with reference to this, so what you have is 2 by n P2 by P1 whole to the power 2 by n minus 1 minus of n plus 1 by n P2 by P1 whole to the power n plus 1 by n minus 1, and this will be equated to 0. Okay, and what we saw was this can be written as 2 by n P2 by P1, so that will be 2 minus n by n, and this can be equated to n plus 1 by n whole to the multiplied by P2 by P1 whole to the power n plus 1 minus n. So you will simply have 1 by n here. Okay. And if we take P2 by P1 on one side, by manipulating the powers, you have 2 minus n by n, to be precise, divided by P2 by P1 whole to the power 1 by n. We get n plus 1 by n multiplied by n by 2. So that is how we get n plus 1 by 2 on the right hand side. And let's see what we get on the left hand side. So we have P2 by P1. The power is 2 minus n by n minus 1 by n. So that makes it 1 minus n by n. Okay, so this makes it P2 by P1 whole to the power 2 minus 1 is 1. The denominator is common as n. And on the right hand side, I have got n plus 1 by 2. So now P2 by P1 is n plus 1 by 2 whole to the power n by n minus 1. So this is what we got. Okay, so just try to remember this term. P2 by P1 is n plus 1 by 2 whole to the power n by n minus 1. Okay, so now if you go back to this line, remember it is n plus 1 by 2 divided whole to the power n by n minus 1. Okay, n by n minus 1. And this is what we got. And we are getting n plus 1 by 2 whole to the power n by n minus 1. Right? Okay. Are you guys able to find any mistakes in this derivation? If so, you
So
can
it will be n by 1 minus n, sir. n plus 1 by 2 whole power n by 1 minus n.
Which step?
So the final step which you have marked, which you have encircled, p2 by p1 equal to n
Yeah,
plus 1
yeah.
by 2.
It's 1 minus n. Yeah. Yes, you're right. The same mistake I made yesterday. You're right. So this is, so here you have got 1 minus n by n. So that will be n by 1 minus n, not n minus 1, 1 minus n. Yes, you're right. Okay. So here what we have is, so what we have here is 2 by n plus 1 whole to the power n by n minus 1. And what we have got is n plus 1 by 2 whole to the power n by 1 minus n. Okay. So now what we can do is we can invert this. This fellow is equal to 2 by n plus 1 whole to the power n by n minus 1. Okay. So when I invert this, so how will this get inverted? So when I invert this, this will actually become 2 by n plus 1 whole to the power 1 minus 1 by n. This is what it will become. Okay. But I can also write this as 2 by n plus 1. If I take a minus sign, it will become minus 1 plus n divided by minus n. And to compensate for this minus, I can write this as 2 by n plus 1 whole to the power n by n minus 1. Is this correct?
So the powers actually they don't reciprocal, no sir. Powers in the division, only the base in the fraction they get reciprocal, no sir. N by n minus 1, if we take with that minus, only the base gets inverted, no sir.
So can I write it like this? 2 by n plus 1 minus of n minus 1 by n. Okay? Can I write it like this?
So the powers, the
No, no,
fractional
no, no.
term of the power, they don't get inverted, no
See,
sir. It will
see,
remain n by 1 minus n, no sir, or n by n minus 1.
see, we are not changing anything. We are just manipulating it, right?
Yes, sir. Even in this step in the process, that doesn't get actually inverted, no sir. The power,
See, what is x to the power minus 1? That is 1 by x,
yes,
right? Okay. So when I write um, what we have right now in our hand is n plus 1 by 2 whole to the power n by 1 minus n. This is what we have. We
yes,
have
sir.
actually. Okay. And uh,
So by taking the minus in the denominator, it becomes n by n minus 1. So to with that minus, we can actually invert the base 2 by n plus 1 whole power n by n minus 1.
yeah, I'm just saying it in the reverse order, right?
Yes, sir.
So here your n plus 1 by 2, you have this. So if I just introduce a minus here, it doesn't change anything mathematically, and so I can write this as minus of n by n minus 1. Is that correct? Okay. And now I can invert this as 2 by n plus 1 whole to the power n by n minus 1. Okay, right?
Yes, sir.
So we manipulate the power and then we invert it, not by inverting it and then manipulating the power. Correct. Okay, so this is how we get 2 by n plus 1 whole to the power n by n minus 1. Okay, and then we substitute this back in our mass flow rate relationship, which is over here. So let us write this here. It's not getting deleted. Okay, fine. So what we have here is m dot equal to a2 times, what was this, n by n minus 1? 2n by n minus 1. So this is 2n by n minus 1, p1 by v1, p2 by p1 whole to the power 2 by n minus p2 by p1 whole to the power n plus 1 by n. So let's check whether it is right. Yeah. And we have got p2 by p1 as p2 by p1 is 2 by n plus 1 whole to the power n by n minus 1. Right? Okay. So now we can substitute for this p2 by p1 and we can get the maximum mass flow rate. So you have got A2, 2n by n minus 1 is undisturbed, and P2 by P1 we get 2 by n plus 1 times n by n minus 1, and there is already a power term 2 by n, minus 2 by n plus 1 whole to the power n by n minus 1 times n plus 1 by n. So all this is inside the square root. So I can cancel out this n and this n, this n and this n. Okay, and I'll get a2 times root of 2n by n minus 1, v1 by v1. This v1 inside the root is specific volume. So this is 2 by n plus 1 whole to the power 2 by n minus 1 minus of 2 by n plus 1 whole to the power n plus 1 by n minus 1. Okay, so now I have got a common term 2 by n plus 1 here, and I also have a common denominator in the powers. So can I manipulate them? Is that possible? So you get 2n by n minus 1 times p1 v1. So you get 2 by n plus 1. So it's like uh, 2 to the power 2 by 3 minus 2 to the power 1 by 3. So what do we get out of this? 2 to the power 2 to the power 2 by 3 minus 2 to the power 1 by 3. What will we do? Can we do anything over here? Is it possible to do anything? We can't do anything in this particular manner. So what we can do is uh, we have 2 by n plus 1 whole to the power 2 by n minus 1. So if we take this 2 by n plus 1 whole to the power 2 by n minus 1 as common on the outside, we will have 1 minus 2 by n plus 1 whole to the power n plus 1 by n minus 1. What we are actually doing is we are dividing this term by this term because this term is removed from this. So when you divide it, so in the numerator you will have 2 by n minus 1. Okay, though it looks a little bit complicated, if you manipulate this power, it will be easy. If you look at this, it is n minus 1 into n minus 1. Okay, which means
So minus signs in between the powers. Minus 2 by n minus 1.
yes, yes, yes. If the whiteboard is there, it would be easy, but it's not getting installed. It will be very lengthy if I write it over here. So that would be m dot max equal to a2 times 2n by n minus 1, no change over here, 2 by n plus 1 to the power 2 by n minus 1. Just hold on. So what we have got here is m dot max. I'm not going to write from the beginning, so I'll just write from where we have stopped. So a2 by root of 2n by n minus 1 p1 v1. Okay, and we have taken this 2 by n plus 1 whole to the power 2 by n minus 1 as common on the outside, and what we have is 1 minus of 2 by n plus 1 whole to the power n plus 1 by n minus 1 minus of 2 by n minus 1. This is what we have got. Okay. So now, if you look at this particular term, so here in the powers, there is a common denominator. So I can add the numerator in the power. So that will give me n minus 1 in the numerator again. So n minus 1 by n minus 1, this particular power term will get vanished. Okay, so you will get a2 times 2n by n minus 1 p1 by v1. We have 2 by n plus 1 whole to the power 2 by n minus 1. And what we have here is simply 1 minus 2 by n plus 1. Just as I said, this numerator will become n minus 1. N minus 1 by n minus 1 will be 1. So you will simply get 1 minus 2 by n plus 1. Okay. And so you will be getting 2n by n minus 1, p1 by v1, and outside we have got 2 by n plus 1 whole to the power 2 by n minus 1. And here, if you open brackets, you will have n plus 1 minus 2 by n plus 1. Okay, and so if you further manipulate on this, you'll get 2n by n minus 1 times v1 by v1, 2 by n plus 1 whole to the power 2 by n minus 1. And here what we have is minus 1 by n plus 1. N minus 1 by n plus 1. Okay. And now I can cancel out this n minus 1 and this n minus 1. So finally, what we have is 2n by n plus 1. We have got p1 by v1. And then we have got 2 by n plus 1 whole to the power 2 by n minus 1. So this is the equation that we get for m dot max. Okay. So this is what we have for m dot max. And this is what we are seeing in the slides as well. Okay, so quite tricky but simple. The only thing is removing that 2 by n plus 1 outside. So in the event of removing it, so you are subtracting the power minus 2 by n minus 1 for the second term. So we will be able to get this particular point. Okay. So is the slide visible now? And similarly, you can substitute for P max. So V2. So for P2 by P1, here you can get. I'm not able to see the slide. Wait, I'll stop sharing and get. So here you have got a term for V2. Okay. So here you have the term for V2. So here again, for P2 by P1, you can replace it by 2 by n plus 1 whole to the power n by n minus 1. So you will have 1 minus 2 by n plus 1. The numerator term will vanish because you'll have n by n minus 1. Here you have got n minus 1 by n, so that will vanish. You'll simply have 1 minus 2 by n plus 1. So that will be n minus 1 by n plus 1. So you'll simply have 2n by n plus 1 multiplied by P1 V1. Okay, so that will be your V2 max. 2n by n plus 1 multiplied by P1 V1. Okay, so you can substitute that and check if you are able to get V2 max. And we have already seen this critical pressure ratio as well. Okay, and now let's talk about this significance of the critical pressure ratio. Okay, so here, so let's take this as the entry. And slightly higher. So this is your entry point, and we call this as P1. And this pressure, let's say P2, or here they have called it as PB, and you can see that this is called the back pressure. Okay, and here, just like we have seen P2 by P1, now we are seeing something called PB by P1. Okay, so this is the exhaust region, and this is your nozzle. Entry to the nozzle is P1, and the exit at the exit we call it as the back pressure, or so far we called it as P2. Now let's call it as PB. And what we find is, if this back pressure is equal to the inlet pressure, okay, PB by P1, if that is equal to 1, if this pressure is equal to this pressure, there is no pressure difference at all. If there is no pressure difference at all, then the velocity will be 0. Only when there is a pressure difference, you will have a flow. If there is no pressure difference, then there is no flow. That means no velocity. Okay. So when PB by P1 is equal to 1, so PB by P1 is in the x-axis, and you have the mass flow rate on the y-axis. So when PB by P1 is equal to 1, you can see that the corresponding mass flow rate here is 0. Okay. So now what we do is, I am going to reduce my back pressure to 2. So I am moving towards the left, which means I am lowering the back pressure. So when the back pressure is lowered, say to the condition 2, to the state point 2, now you can see that there is a flow that is taking place. Your mass flow rate value has increased on the y-axis. So the corresponding mass flow rate has increased. So initially it was 0 when back pressure is equal to inlet pressure. There is no flow that is taking place. When the back pressure has dropped, you can see that there is an increase in the mass flow rate. And when you are further decreasing the back pressure to the state point number 3, you can see that the maximum mass flow rate has been attained. And if you further try to decrease the back pressure to state point 4 or state point 5, you can find that there is no change in the flow rate. The mass flow rate does not change. Your mass flow rate, there is no change in the mass flow rate. So that condition in the nozzle is called as choking or choked nozzle. Okay. So your maximum mass flow rate has already been attained. You cannot increase the mass flow rate further. Okay. So this pressure at which the maximum mass flow rate takes place, this is called as, and this pressure ratio is called as the critical pressure ratio. Okay. So what is the significance of critical pressure ratio? It is at this particular pressure ratio that you have the maximum mass flow rate. And we are able to see that we need to have that for the maximum mass flow rate where the back pressure is minimized when compared to your inlet pressure. Okay. So that is something which you should keep in mind. So whether they ask this in your 2-mark question or whether it appears in your question paper, this is fundamental with reference to the flow inside the nozzle. Okay. Then they are talking about the effect of irreversibilities in nozzle efficiency. We have already talked about this irreversibility in turbine and pump in case of the Rankine cycle, and that is nothing but the deviation of the process from the isentropic condition. Actual processes are not isentropic, we know that. Actual processes are irreversible, and here in nozzle also, it is not possible to have an isentropic flow. Then what are the causes of irreversibilities? And that is because of friction. And where does this friction happen? Between the fluid and the wall surface and within the fluid itself. Okay. So these two conditions enhance your friction. And because your friction is enhanced, that is going to be a source of irreversibility, deviating the process from the isentropic condition. Okay. And the maximum deviation, it is seen not in the convergent portion. So here they are talking about, you can see that the effect of friction in the divergent portion of the nozzle. So that is between 2, 3. So 1, 2. So this 1, 2 is the converging section. And you know that point number 2, that is going to be your throat. And this is the diverging portion. Okay. In the converging portion, your pressure drop is more and your velocity is increasing. Okay. And so the friction that you will see here is less. Okay. Whereas the friction that you see here is more. So in the divergent portion is where you will see the effect of friction more. So the deviation is shown here between the process 2, 3. So 2, 3s is going to be isentropic. So 2, 3s is isentropic, and the deviation you can see, that is your actual process. Okay. So if you take a convergent divergent nozzle, the area of the convergent portion is usually lesser than the area of the divergent portion. So here the amount of fluid that comes into contact with your walls. Okay, so this region, the walls of the nozzle, which I am showing with the blue. So this is less. The friction between the fluid and the wall is less in the convergent portion as compared to the friction that happens in this region. Because the area of the divergent portion is more, you are going to have more friction on the divergent portion. So that is one reason. And that we can see as nozzle efficiency. So in the nozzle efficiency, The definition is actual enthalpy drop divided by the isentropic enthalpy drop. And you can see that. So the actual enthalpy drop is lesser. You can see, so this is going to be H2 and this is my H3S. Okay. So this is my H2 and H3S. So H2 minus H3S, this difference is greater than, you can see H3. H3 is relatively above H3S. So this difference is greater than H2 minus H3. Okay. So your actual enthalpy drop is H2 minus H3. Your isentropic enthalpy drop is H2 minus H3S. Okay. The other way which you can say this is actual kinetic energy at nozzle exit divided by kinetic energy at nozzle exit for isentropic flow. Both are one and the same. Okay. And this you can call as V3 squared by 2 whole divided by V3S squared. Whenever I use capital V, that is for velocity. So V3 squared by 2 divided by V3S squared by 2. So you have 2 on both the numerator and the denominator, that which can be cancelled out. So this is the effect of friction in case of your nozzle. Okay. And this we can use in our problem solving. And these are all the happenings because of the friction. The reduction in enthalpy drop, which we have already seen. So from H2 to H3 it is now just H2 minus H3. So there is reduction in enthalpy drop. And whenever there is friction, there is going to be heating. Okay. So in nozzle, heating is not preferred. What is preferred is the increase in the velocity. So some reheating of fluid also takes place because of the friction. Then you have reduction in the exit velocity because some of the energy which needs to be converted into kinetic energy is getting converted into a heat energy because of the friction. So that obviously reduces your exit velocity. And that increases your specific volume. Whenever there is a heating takes place, there is going to be some amount of expansion which results in an increase in specific volume. And obviously, this is going to decrease your mass flow rate, which is not desirable. Okay, so these are the effects of friction. And there is two other terms called coefficient of nozzle velocity coefficient and coefficient of discharge. Coefficient of discharge you would have already come across in fluid mechanics, actual mass flow rate by mass flow rate with isentropic flow. And CV, this is the nozzle velocity coefficient, which is defined as actual velocity at nozzle exit divided by velocity at the nozzle exit with isentropic flow under the same exit pressure. Okay, and so you can also define this as V3 divided by V3S. Okay, initially we saw nozzle efficiency as V3 squared divided by V3S squared. So when this squared term is removed, so that means V3 by V3S is square root of your nozzle efficiency. So that is how you get square root of nozzle efficiency. Okay. So this is the actual mass flow rate divided by mass flow rate under the isentropic condition. Okay. So these are all some of the definitions which will be useful to us when we install steam nozzles. So here there is one example. So a nozzle is to be designed to expand steam at the rate of 0.1 kilogram per second from 500 kilopascal and 210 degrees centigrade to 100 kilopascal. Inlet velocity of steam for a nozzle efficiency of 0.9, determine the exit area of nozzle. Okay, so for this you have to take your Maillard chart. Oh, I will not be able to mark it today, so you guys have to let me know. Okay. What happened? Nothing is visible. The values are not there. What happened to this Molière chart? Yeah, now it is coming. Okay, so the given condition is 500 kilopascal, which means 5 bar, but here everything is in um, megapascal. So it is zero point 0.5 megapascal and 210 degrees centigrade. Okay, so zero point 0.5 megapascal line is over here. I will not be able to mark it. I'm not able to use this in here. Let me check if I can use it. Most of you are not having the. No, it's not working. So you guys have to tell me. Okay. So I'll show you the Malio chart, but you guys are going to give me the earlier. Okay, it's visible. So what is given to us in the problem is zero point 0.5 megapascal and 210 degrees centigrade. Okay. So Kaushik, can you help me with identifying the value for P equal to zero point 0.5 megapascal? So that is over here. I'm not sure if you are able to see the pointer. Yeah, you are able to see. So P equal to zero point 0.5 megapascal line is over here, and you have to move on it till you reach 210. Okay.
So enthalpy is 2875 approximately.
Yeah, 2875. Okay. So let's write it as 2875 then. I'm not able to delete this as well. This is also a problem. I have to find a way for this. So H1, we are getting H1 as 2875 kilojoule per kilogram. But before that, let's draw the HS diagram for this. So that is what we are using right now, the Molière chart. Okay. So you can simply call it as HS diagram, and you can just draw two lines for the pressure lines, just like you have over there. So this is your zero point 0.5 megapascal line, and this is your 100 kilopascal line. and this is say point 1, from point 1 to 2s. Okay, and they have said nozzle efficiency, that is why we use the word 2s. Let me use another color, maybe blue. So this will be 1 2, the actual process. Okay, 1 2s is isentropic, 1 2 is the actual process, and they have given the nozzle efficiency as zero point 0.9. Okay, so we have identified point number 1, which is for which H1 is 2875. So for the same thing, can you get me the value of entropy by looking at the same Ollier chart? So H, you looked at the y-axis. For S, you can look at the x-axis. What is S1?
7.1.
Yeah, good. So this is 7.1 kilojoule per kilogram Kelvin. And can you get the value of H2S? You have to draw a straight line from 1 till you reach zero point 0.1 bar, in this case 0.01 megapascal. You have to draw a straight line from 0.1 till you reach 0.01 megapascal. Is that available in the Mollier chart?
2250, sir.
2000? What is the value? What is the value of H2S?
2250, sir.
250.
Yes, sir.
2250. Okay, but the book value is higher. Um, but anyhow, so let's proceed with whatever values we have got. Okay, and what is the efficiency of the nozzle? So in this particular case, they are simply talking about the entry and the exit, which means it can be either a, so have they mentioned that whether it is a converging nozzle or a diverging nozzle? No, they have not mentioned. They have simply said it is a nozzle, and they are saying that the entry is 500 kilopascal and 210, and the exit is 100 kilopascal. Okay, so if we are saying so, we can assume that it is a converging nozzle or a diverging nozzle, where there is only an entry and the exit. There is no throat region over here. Okay, and they have said the nozzle efficiency is 0.9, and we have seen the definition for the nozzle efficiency is actual enthalpy drop, actual enthalpy drop divided by isentropic enthalpy drop. Okay, so that is your definition. So that is your definition. And what is the actual enthalpy drop here? That should be H1 minus H2. And what is the isentropic enthalpy drop? That is H1 minus H2S. Okay, and we have got the value of this H1, we have got the value of H2S, and we know the value of this eta n, which is 0.9, so we can get the value of H2. So I am going to substitute the value of H1 minus H2, so that is 2875 minus H2 divided by 2875 minus 2250, and this fellow is equal to 0.9. So can any one of you calculate this and let me know the value of H2, because this value is going to be different from what is there in our textbook. Okay. So it is 0.9 0.9 multiplied by
2312.5.
2312.5. Okay, so he has calculated it 2312.5. So that is our H2. And what is the question? The question is determine the exit area of the nozzle. Okay, so if I want to find the exit area, I have to use the formula m dot s rho a v, or you have to use the formula a2 v2 by small v2. Okay, so we need to get the value of any of these, sorry, all of these, to get the value of area. So they have given the value of this mass flow rate. Mass flow rate is given in the problem as 0.1 kilogram per second. That is given to us in the problem. And is it possible to find out the value of this velocity? So this capital velocity is nothing but 44.7 root of h1 minus h2, 44.72 if you want it. And when you use this formula, this 44.72 has already taken care of this kilojoules. So don't once again multiply it by 10 to the power 3. Okay, so you should be very familiar with what formula that you are using. If you are using 44.72, directly substitute it in kilojoule per kilogram. So this is 2875 and H2 is 2312.5. So can you help me with the answer for this? So let me know if it is 1060.16.
Yes, sir.
Yes, sir. Is it very high? 10. Oh, I forgot the answer. 1060.63. 1060.63. And what else we need to know is small v2, specific volume. So for that, I have to take you to the Mollier chart. In this Mollier chart, there is no possibility to find the value of small v. In some Mollier chart, it is possible to get the value of small v. Okay. So there is no other go. We have to find it out using the steam tables. Okay. So now what you have to check is, okay, so there is no other go. We have to use the steam tables for this. Okay. Now you have found this H2, the value of H2. The value of H2 is 2312.5 kilojoule per kilogram. And there is a pressure that is given as 0.1 bar. So Kaushik, go to steam tables, saturated pressure table. For pressure P2 equal to 0.1 bar, check the values of HF and HG. Is this value 2312.5 between HF and HG? Check that. For a pressure of 0.1 bar, check the values of HF and HG and see if this value 2312.5 lies between HF and HG. What is the value of HF and HG?
It's 100 kilopascal is 1 bar. No, sir?
Yeah, sorry. So it's 1 bar.
So
for
that
1
would be a
bar,
mistake for the enthalpy and entropy also, sir.
sorry, I don't get you.
So the value which we got, you said was lower than the book value, no, sir?
Yeah.
Because I took 0.01 megapascal in the chart.
So 100 kilopascal is 1 bar.
0.1
1 bar is,
megapascal we should have
yeah, it
referred.
should be 0.1 megapascal. Or is my definition, yeah, here we have written it 100 kilopascal. How come we made this mistake? So check what value you get for H2S, then that will change everything. Okay, leave it, Kaushik. Leave it. We have made a mistake, but let's not go and correct that. Okay, that correcting that will once again take a lot of time. Okay, but anyhow, we have to get the value of V2. So at least let's be familiar with the process. Then we will move on to the second problem, and there we will try to do it correctly. Okay, so for 1 bar, just let me know if this 2312.5 is lying between HF and HG. Or let's change the problem as 10 kilopascal, no problem. So for 0.1 bar, Kaushik?
Yes, sir.
So for 0.1 bar, check if 2312.5 lies between HF and HG or not. Let's take it as 0.1 bar itself. Because we have proceeded this far, HF should be 191.8. What about HG?
2584.7.
2584.7. Okay, so that shows very clearly that this value lies between HF and HG. What do you mean by that? This particular condition is lying on the liquid plus vapor region. That is what we can infer. Okay, so what we can do is we can get the value of x2. So you can say H2 is HF2 plus x2 into HFG2. So what is the value of HFG? What is the value of HFG? So that should be the difference of 2584.7 and 191.8.
2392.9.
2392.9. So 2392.9. Can you just get me the value of x2? 2392.9. So x2 into 2392.9. So this will give me the value of x2. Closer to 0.8 or 0.9, in that range it should be, I believe. Or maybe 0.7. How much do you get?
So 0.886.
0.886.
886.
So let's call it as 0.89. Okay. So now you have to get the value of VF and VG at 0.1 bar. VF should be 0.001010. We have done this a lot of time. I think it would be in memory for everyone. What about VG? What is the value of Vg at 0.15?
675, sir.
Point
14.675.
14.675. Okay. So 14.675. Very huge. So now we have to find out V2. V2 is Vf2 plus x2 times Vg2 minus Vf2, that is Vfg, because we don't have Vfg directly. Very rarely in some steam tables they give Vfg also. So can you get me the value of this V2? Why I'm solving this is, if suppose you don't know how to get the value of V2, this is how we have to solve it. It is for that reason we are doing this. Check what we get for V2. For the next problem, we will go to paint. That will be easy. How much do you get here? So what's the answer for that? Have you solved it?
13.2076.
2.2076. Okay. So our V2 is 2.2076 meter cube per kilogram. Okay. So our M
So
dot is
13.207.
13 point.
Yes, sir.
Okay. So this is 13.2076. So your M dot is A2 V2 by small v2, and what we require is capital A2. That is M dot V2 by capital V2. M dot happens to be 0.1 kilogram per second. Small v2 is 13.2076 whole divided by 1060.63. How much do you get? You'll get something in meters squared. So that should be your area. What is the area? What is the area at the exit? What is the area at the exit? கையெழுத்து வாங்கணும்னா வாங்கிக்கோ. What is the area at the exit?
1.245 into 10 power minus 3.
1.245 into 10 to the power?
Minus 3.
10 to the power minus. Okay, so this is your area at the exit. Okay, so I'll show you the solution for this problem. So this is what the solution is. So from the Malia chart, they are able to get H1 and S1, H2S and S2S. S2S is same as S1, and this is not a big deal for this because we are using the Malia chart. When we use the steam tables, we have to use S1 equal to S2 to get the value of the dryness fraction if your point number 2 lies in the liquid plus vapor region. Okay, and because we have mistakenly taken Instead of 1 bar, we have taken it for 0.1 bar. So our value is different from the book value. Okay. So here, this is your isentropic enthalpy drop. This is your actual enthalpy drop. And this is your H2. So from the Mollier chart, they have estimated 0.97. Okay. So this is smart. Okay, so from the Mollier chart, you will be able to get the value of 0.97. Okay, so for x2. Kaushik, was that point number 2 in the liquid plus vapor region when you looked at the Mollier chart? It should be. Was it in the liquid plus vapor region? Kaushik?
Yes, sir.
So can you check what dryness fraction was there from the Mollier chart?
0.86.
0.86, and we got 0.89. So not a big difference, not much of a difference. So once you get X2 directly from the Mollier chart, then you can go back to the steam tables and get V2 is equal to Vf2 plus X2 into Vfg2. That is the smart way of doing it. So we will use that in the next problem. Okay, so then they estimated the velocity and they have calculated the exit area. So this is what they have done in the textbook. Okay, so this is problem number 2. Let me see if I can copy paste this. Okay, it's not getting pasted. So here we have a convergent divergent nozzle. Okay, which means you have got an entry, you have got a throat, you have got an exit. The entry is at 2 megapascal and 400 degrees centigrade with a negligible velocity and mass flow rate of 2.5 kilogram per second. The exit pressure is at 300 kilopascal, so that means they are talking about the exit, not at the throat. So throat is something which we have to find out. We don't know what pressure is there at the throat. The flow is isentropic between the nozzle entrance and throat, and overall efficiency is 93%. Overall nozzle efficiency is 93%. Are you able to understand what these guys are telling? Okay, so they are saying that, so let's draw the HS diagram here. So drawing HS diagram is not a big deal. The first pressure that they are talking about is 2 megapascal. Okay, and from here there should be another pressure which they have not mentioned, and they are saying that this process 1-2 is isentropic. The flow is isentropic between the nozzle entrance and throat. This 2 megapascal is the entrance. This point number 2 is the throat. And then they are saying that this is your pressure P3, which is given as 300 kilopascal. This is point number 3. And they are saying that this flow is not isentropic. They are only saying the flow is isentropic between the nozzle entrance and throat. And they are saying overall nozzle efficiency is 93%, which means they are saying that there is going to be a deviation from the isentropic flow when The flow takes place between the throat and the exit. Okay, so your HS diagram has got 3 points 1, 2 and 3 because it is a convergent divergent nozzle. So this region is converging, this is the throat, and this region is the diverging portion. So what are all the given details? So P1 is 2 megapascal, T1 is 400 degrees centigrade, and the mass flow rate is given as 2.5 kilogram per second, and the exit pressure is P3, which is 300 kilopascal. Let's not make the same mistake which we did last time. It's 3 bar. Okay, and the nozzle efficiency is 0.93, and this is applicable only for the diverging portion. Okay, so with this given details, so let me take you to, so I have already shown you the HS diagram, but just for our reference for the problem, we can say HS. This was pressure 1, pressure 2, and pressure 3. And this is 1, 2, and 3. And this was given as 2 megapascal and 400 degrees centigrade. And nothing is said about P2. P3 is 300 kilopascal, which is 3 bar. Okay, m dot is 2.5 kilogram per second. The nozzle efficiency is given as 0.93, and this is only for the diverging portion. Okay, so now once again I need the help of someone. So you have to look from the Mollier chart the value of H1, which is 2 megapascal and 400 degrees centigrade. Get me the value of H1. What is the value of H1? What is the value of H1 for 2 megapascal and 400 degrees centigrade? Not yet trace the point.
240, sir.
3240, sir.
Okay, 3240 kilojoule per kilogram. Okay. See, now if you have to trace the point to 2, you need to know what pressure it is. Okay. Without knowing the pressure, you will not be able to draw a straight line till it reaches point number 2. So we need to know what this P2 is. Okay. But what we do know is, can you guys confirm me that this point number 1 is in the superheated state?
Yes,
This
sir.
point number 1 is the superheated state. Okay. So because state point number 1 is in superheated state, I can use P2 by P1 equal to 0.546, which we saw when we said your P2 by P1 is 2 by n plus 1 whole to the power n by n minus 1. We derived this formula and we substituted n equal to 1.3 for superheated steam, and we end up getting 0.546. Okay, so this result is already available to us. This is something which you need to keep in mind. Uh, Keeping the formula is okay. 2 by n plus 1 whole to the power n by n minus 1, and you can remember the values of n for the different states of steam. Okay, so your P2 is 0.546 times P1, which is 0.546 times P1 here is 2 megapascal or 20 bar, however you want to write it. So how much do you get for P2? So can you get me the value of P2?
10.92 bar.
So that is 10.92 bar, or we can say 1.09 megapascal, approximately 1 megapascal. Okay, so now you can look at the Mollier chart. So once again, from Mollier chart, from point number 1, now you can draw a straight line till it reaches 1 megapascal. So from 2 megapascal to 1 megapascal. I am right, right? Okay. So from earlier chart, get me the value of H2 in kilojoule per kilogram. So one of you can let me know of the value. So what's the value of H2? What's the value of H2? How come we have got so many participants today? There are 63 students here. चलो परवाले चलो इन दोनों 5 minutes. So many people are attending.
3050, sir.
Yes, how much is H2?
3050.
3050?
Yes, sir.
Okay, fine. So is this in the superheated or is it in the liquid plus vapor region?
It's a superheated, sir.
It is in the superheated state. Okay. So for this, can you get the corresponding temperature? What is the corresponding temperature for it? Maybe it is between two temperatures, 400 and 450, something like that. So you can find the intermediate temperature. Are you able to find the temperature? You have got temperature lines, right?
It's 300 degrees Celsius.
Good. So that makes the job simple. Okay. So now what you can do is we can assume this to be 10 bar, but I'm not sure. So just check your steam tables. So from steam tables, table number 3, specific volume, superheat specific volume table. So for pressure P2, do you have 11 bar in the column? In the pressure column, do you have 11 bar? Table number 3. Do you have 11 bar, Kaushik?
Yes, sir.
Yes. Okay, then fine. So let's take 11 bar then. Okay. So for 11 bar and 300 degrees centigrade, get the value of specific volume.
Point 2339.
Point
2339.
Very good. That's very close. So for P2 equals 11 bar and temperature T2 equal to 300 degrees centigrade, we are able to get V2. Okay, so you should know the procedure. The procedure is very important. So from Maillard chart, you can get the enthalpy and temperature, and using the temperature and pressure, you will be able to get the specific volume. Why do we need this? Because they are asking us to find the throat area. Okay, so if we have to find the throat area, the formula is m dot equal to A2 V2 by small v2. So what else is required is capital V2. Capital V2 is 44.7 root of H1 minus H2. So get me the value of this. So 44.7 root of H1 is 3240. H2 is how much? 3050. So this will give you the answer in meter per second. So your A2 is M2 times V2 divided by capital V2. And mass flow rate here is 2.5 kilogram per second. Small v2 is 0.2339 whole divided by, what is your capital V2? How much are you getting? How much are you getting?
8,493.
8,493.
93, sir.
It's very huge.
Sir, 616.14.
Yeah, that should be right. 600 and
16.
616.14. Is it? 616.14. So now you will be getting something in meter squared, maybe 10 to the power minus 3 or 10 to the power minus 2. Okay, so one part of the question is solved. So you are able to compute the throat area. Then what you have to do is get the value of H3S. Remember, this is 3S, and they are saying that there is a nozzle efficiency, so that should be a 3. So get H3S either from, you can get it from Maillard chart. So from the Maillard chart, you have to look for 3 bar, which is 0.3 megapascal. So can you get that? Is it possible? Can you get the value of H3S, Kaushik, from the Maillard chart for 0.3 megapascal?
Yes,
Is it
sir.
possible to get that?
Yes, sir.
Just let me know of the value. With that, we will close this. Because the procedure is going to be the same. So I'm going to ask you to do this as homework. So what is the value? What is the value of H3S? Draw a straight line from 2. How much do you get?
$2,775.
Okay. Okay. So now that you know the value of H3S, you use the nozzle efficiency and get the value of H3 and follow the same procedure. Okay.